very good morning, dear student friends. Today we are going to discuss on demonstration of wind power generation of the course titled Smart Grid Basics to Advanced Technologies. Now we are going to discuss on a test bed for the demonstration of wind power generation, and as you could see, this is the brief introduction to wind power generation. Ideally, we capture the kinetic energy through wind turbines and through gearbox to the generator and through power converter to the transformer, and hence the energy is being fed to the power grid. A typical wind power generation convert kinetic energy of the wind to the useful electrical energy. The aerodynamic modeling equations of the wind turbine helps to assess the performance of the wind turbine with respect to the varying wind speed. The power generated from the wind turbine is a function of the power coefficient and the wind speed. With the recent development in the semiconductor technology in the field of wind energy, the less productive fixed type wind generators are being replaced by the partially variable and completely variable types. Among the variable type of generators, the DFIG wind system, which is one of the partial variable type, is known for its cost effectiveness due to the scale down in the converter size. The power converters are rated to handle complete range of wind speed variations. Now focusing on doubly fed induction generator, so called as DFIG WPG, the schematic representation of the DFIG wind system along with the power flow is shown in this slide. As the name suggests, the doubly fed induction generator is capable of feeding or observing power in two directions. The stator part is directly exposed to the grid, which works at fixed voltage and frequency. Henceforth, it is mandatory that the stator of the DFIG is compelled to operate as per the grid norms. However, this is only possible if the rotor operates at synchronous speed. In a practical scenario, the speed of the generator keeps on varying from the sub-synchronous speed, say in the morning hours when the wind speed is low, to the super synchronous speed in night hours when wind speed is extensively high. Thus, with the conventional induction machine, it is not possible to inject power from the wind system to the grid. With the DFIG setup, it is possible to inject power at varied wind speed into the grid via stator over a speed range of plus or minus 30%. During the sub-synchronous mode of operation, since the wind speed is less, the positive slip power is drawn from the grid via rotor side converter, grid side converter, combination to the rotor, such that the prescribed power at the grid frequency could be injected from the stator end. By neglecting the losses of the back-to-back converters, where Pg equal to Pr, we can say that the power at PCC is equal to the addition of the power generated by the wind turbine, that is the stator power and the rotor power. Here P equal to PS plus PG, that is the summation of PS and PG. During the subsynchronous mode of operation, rotor speed is less than synchronous speed and thus the slip is positive. Similarly, during the supersynchronous operation, the excess power from the rotor in terms of negative slip, power flow out from the rotor via RSC and GSC combination, thereby helping to follow the grid norms as per the nominal values. Whereas, during the synchronous mode of operation, there is no power injected or absorbed from the rotor and the entire power flow from the wind system is transferred to the grid via stator itself. In summary, by controlling the RSC and GSC, the DFIG wind system can be made to function in all the three modes of operation. Now, focusing on the hardware demonstration of the setup of wind turbine, grid connected operation of the DFIG setup. Now, before going into the demonstration, let us have a look at the overall hardware connections. DFIG hardware setup consists of three units mainly. The first one is a wind emulator, DFIG, and back to back voltage source converter. The laboratory setup of DFIG is basically a slip ring induction machine coupled with DC motor. This DC motor of rating 2.5 kilowatt, 220 volt, 10 ampere, which behaves similar to prime mover and is controlled by chopper control, providing different wind characteristics. For obtaining the wind emulator, the wind characteristics along with the wind turbine action is mimicked with the help of a buck converter. The DC motor output is controlled via armature voltage control, for which the semicron IGBT stack is being used. An inductor and a capacitor is used to form the buck converter. The control strategy for buck converter is as shown in the schematic diagram. Now, the DFIG control, so called wind emulator, it can be noticed that the wind power, which is half of rho A Cp V cube, in the control scheme is calculated by taking input wind velocity and pitch angle. Here the Cp is the power coefficient which is dependent on the pitch angle and tip speed ratio. Further, the wind power is divided with the measured speed of the rotor to generate the reference torque. The motor reference current is obtained by multiplying the torque reference with the motor constant of value K, which is equal to 4.16 in our case. The current reference is then compared with the actual current of the DC motor. The compared result is sent to the PI controller, thereby obtaining the switching pulses. Now, the induction generator of 2.2 kilowatt rated and is operated through the field programmable gate array FPGA based controller. Vivect FPGA controller of firmware version WCU 10081E is used, which is capable of sensing 8 voltages and 8 current signals along with 8 PWM pulses. While the stator of the slip ring induction motor is connected to the power amplifier via a switch, the switch is initially open and is further closed when the stator voltage and phase angle is synchronized with the voltage and phase of the grid and phase angle using the rotor side converter. After synchronization, RSC regulates DFIG to operate in the speed power control mode. Rotor of slip ring induction motor is connected to the RSC, which is controlled in the FPGA platform. Now, if you look into the DFIG control through rotor side, field oriented control FOC established on the vector control is enlisted for D and Q axis control of rotor current. The maximum power point tracking MPPT is implemented using perturb and observe P&O method by estimating MPPT reference rotor speed at particular wind velocity, regulating the Q axis of the rotor current IQ RSC. Now, the D axis part of the rotor current is governed for managing the stator power factor. This is done by introducing reactive power for smooth variation. Further, the reference voltage is converted to the ABC frame to generate the PWM signals, which is fed to the RSC switches. The RSC is connected to GSC via a DC link, and the job of the GSC is to maintain the DC link voltage. Now, looking into grid side control, the generated DC link voltage when compared with the measured voltage of DC link generate error that is processed through PI controller to obtain D axis reference current. The measured GSC current D axis component tracks the reference value with the PI controller to obtain the reference D axis voltage, while the PI controller dealing with the Q axis component of GSC current is assigned to regulate reactive power injection. Now, the software which is available through Vivect suite for FPGA controller that run on HDL coder, in this platform we provide the governing variables value. First, we connect the Vivect via a LAN cable to the PC and connect the supply voltages. The supply voltage we give by power amplifier of rating 15 kilovolt ampere and 50 hertz. The 3-phase voltage is set in the amplifier 140 volt to get line to line voltage of 240 volts. The grid voltage is reflected in the software due to presence of voltage sensor at that point. The main and the rotor branch circuit breaker is switched on and the DC link is charged initially to 340 volts. Then we enable phase locked loop and check the reference theta with the phase A voltage. Once the DC link is charged, we enable the GSC control to maintain the desired DC link voltage, which is set to say 30 volt greater than DC link voltage, that is close to 380 volts. We see that GSC tracked the DC reference voltage and measured DC link voltage is read as 385 volts. Now, the next step is to enable DC motor control to run the DC motor to provide wind characteristic in the rotation. Here, we vary the duty of the chopper gradually to make the motor run at more than 900 RPM. We are varying the duty and notice that speed is keep on increasing. We can check the rotation here in the speed panel. We see the DC motor is driving the induction machine. Next, we provide the PI value of the rotor side control and enable the control loop. The RSC first is used to build up voltage in the stator side and then match the phase difference of the grid to the stator till they align for the synchronization purpose. Now, we will increase the reference value to match the stator voltage magnitude with the grid voltage using the D-axis control of the rotor. In this process, we also observe that the rotor current is also increased as it takes current from the grid to build the stator voltage, as from the relation the stator power is 1 by slip times the rotor power. I repeat, in this process we also observe that the rotor current is also increased as it takes current from the grid to build the stator voltage, as from the relation the stator power is 1 by slip times the rotor power. The slip is varied plus or minus 30%. So, small current injected to rotor side results in a larger voltage across the stator. Then we vary the Q axis of the RSC to vary the theta. We change the reference till theta is matched. If we see the grid and stator voltage, we see the waveform almost overlap with one another. After voltage get matched in the software, then we check the contactor of the grid side and stator side and ensure that the voltage across the contactor in multimeter is less than 20 volt. Here we are getting a value of less than 10 volt across all three phases. By ensuring voltage is less than the contactor connecting the stator and the grid connection is closed, and then the synchronization is done by enabling sync done in the software simultaneously. Now, the control of RSC is changed from synchronization operation to power speed control mode. Here we see that the 3-phase rotor power is sent. Now, we enter the speed control mode and vary the wind speed to vary the rotor speed. Here we demonstrate the DFIG in 3 different operating modes. Number 1, subsynchronous mode, 2, synchronous mode, and 3, supersynchronous mode. Now, in case of the subsynchronous mode, the rotor angular frequency is lower than the synchronous angular frequency, where omega r is less than omega s. We consider omega s which is close to 1000 rpm and the slip is greater than 0. The total power to the grid is 1 minus slip times P stator. The stator delivers power to the grid while the rotor receives power from the grid. Next, we slowly increase the speed and bring it in the synchronous mode. The rotor angular frequency is equal to the synchronous angular frequency, where omega r equal to omega s and the slip which is equal to 0. DC current flows into the rotor winding. The total power to grid is P, which is stator power. Only the stator delivers power to the grid. If we further increase the speed of the DFIG, works in the super synchronous mode. The rotor angular frequency is higher than the synchronous angular frequency, that is omega r is greater than omega s, and hence the slips falls which is less than 0. The total power to the grid is P, which is 1 plus slip time P stator. Now, both the stator and the rotor deliver power to the grid. With this, we have today understood how a DFIG wind turbine operates, and thank you for your attention.